Ленечка, здорово.
Do you want to start right now, or is there 1 minute?
Okay, let's introduce speaker. Leonie, can you do that?
Okay, so it's my great pleasure to introduce our speaker for today and hopefully for the next 2 sessions of this seminar. So Gaetan Borot from Humboldt University, Berlin, right? And Gaetan will speak about modern state of art, I would say, in topological recursion and related theories.
So thank you, Leonia, and all the organizers for arranging this series. I'm very surprised there's so many people, 50 participants. That's great.
There will be much more, many more. Don't worry.
So yeah, so the organizers asked me to give some introduction on what is called Airy structures and topological recursion. So the topological recursion has been initially found in matrix models, and that's also where Leonia, was one of the pioneers of that. And then it was developed for spectral curves. So coming from integrable systems, and there it found many applications to various problems of enumerative geometry. And then in 2017,
do you mind listen to it? Yeah, sure.
Kontsevich and Soibelman have proposed revisited a bit. Yes,
I'm sorry. We want to ask all participants to mute themselves. So if you have any questions, please unmute yourself and ask, but please mute yourself. Yeah, I'm sorry for that.
No problem.
I don't understand.
So it was revisited by Kontsevich and Soibelman, who proposed, I would say, a rather simpler framework to have a topological recursion. And so that's the one of Airy structures, and I'm going to start defining this. So roughly speaking, an Airy structure is a collection of linear PDEs in many variables, and which are compatible. And to this, it will be too general. You add a little condition, there's a nice grading, and that's what will make the connection to 2D geometry. So let V be a vector space. I work over C. And I will do as if V was finite dimensional. If V is not finite dimensional, as in the most interesting examples, you have to complete what I write a little bit, but everything works well at the end. And I prefer not to start with a too heavy framework. So assume that all sums you will see converge, or when they act on something, it converge. So if I have a vector space over C, I can form the Weil algebra, which is the algebra of differential operators. So I'm going to fix a linear basis of coordinates. And I can look at polynomial differential operators. And I put some parameter h bar here. And I may want to have formal series in h bar. There's formal differential operators on V. And we can make it a graded algebra by assigning the degree 2 to h bar and the degree 1 to each of the xi. So in particular, the degree of h bar dxi. So d over dxi is degree -1. And so when you multiply by h bar, it's degree 1. So these are all the differential operators that contain only non-negative powers. I mean, terms with non-negative degree. Okay. And an Airy structure. So that's what one calls a quantum Airy structure. So I call that QAS. Is a linear map from V to the Weyl algebra. So for each element of a basis of V, you have a certain differential operator. And you satisfy two conditions. There's a degree 1 condition. So I have my basis of linear coordinates. So let's EI be the corresponding basis of V. And so L of EI, so we simply denote Li, should start with h bar d over dxi plus something that contains only, so it's a sum of monomials, only with degree bigger or equal to 2. So this means that's the degree 1 term. There's no degree 0 term. And I could also imagine that I have some xj here, and that would be degree 1, but I don't want that. So just this trivial differential operator in degree 1 and then higher orders. And then there's what I would call the graded Lie ideal condition, which tells that if you commute Li and Lj, that must be in the ideal up to a shift by h bar spanned by the Li's. So the simplest example would be when L has terms of maximal degree 2. So in that case, what can you have in Li? You must have that in degree 1, and then all the rest must be in degree 2. In degree 2, you have some xx. You may have some x h bar d over dx, some double derivative, so some are a and b, and you may have a constant. So here a, b, c, d are scalars. And that's the general form of an operator satisfying degree 2. So satisfying the degree 1 condition. And then for 2, it puts some constraints on what A, B, C, and D could be. So Li, Lj must be h bar some differential operator, and then it must be in the span of the La. So I must have something of this type. So this thing has degree maximal degree 2. This thing as well. And h bar has exactly degree 2. And as this Weil algebra is a graded algebra, the commutator preserves degree. And since that one has maximal degree 2, well, the only possibility is that this thing actually here is a scalar. For degree reasons. So it means that very specifically to this case where I only consider up to degree 2 operators, the second condition means that you have a Lie algebra. If you consider operators of arbitrary degree, then no, you don't have anything like this. This could be differential operators. And that's why we rather say it's an ideal. And graded just mean that, of course, in some associative algebra, if you consider the corresponding Lie algebra, being an ideal is a bit trivial. But here there's this H bar which is in front. And that makes it non-trivial. So apart from the fact that this, I mean, what is the meaning of this algebraic definition? Well, when you have an Airy structure, you have a corresponding partition function, and that's what usually we're interested in. So there exists a unique f, which is a formal function on V. That means an element of symmetric powers of V star, such that for all I, all the operators we have in the Airy structure annihilate exponential of f. And you have some normalization condition. So we can write f in this way. Somehow, because we're working with formal functions, it just means you have a collection of Taylor coefficients. So I'm going to write FGNs for the Taylor coefficients. And then I may have a certain power of H bar. So this is a general form of an element in here. So there exists a solution, but it's going to be unique once you normalize it properly. So you want that there's no constant term at any order in H bar, and that F01 is 0, F02 is 0. So this is somewhat obvious because it doesn't change if you have a solution. You can always multiply by a constant. So you can always do that, it doesn't harm. But the meaning of the second condition is that you notice that this is something that has degree 2g minus 2 because H bar has degree 2 plus n. And requiring this exactly means that there's only terms of positive degree here. And in particular, it means that exponential of f does make sense. Once you complete the algebra of formal functions, it starts with 1 plus something of positive degree. Okay, so how do we compute this f? Is exactly the way that the topological recursion is appearing in the problem. I'm not going to write down the formula for a totally arbitrary Airy structure. I'm going to stick again to this degree 2 example because it really shows what is happening. So you could say it's a proof of uniqueness. Well, you have a differential equation. So let's just insert exponential of f, where f is given by this, into the differential equation. So what would we get? So I will compute exponential of minus f Li exponential of f, because that's going to be a formal series in h bar and in the x's. And in this, so let's call that I1. I pick some index I1. You want to extract the coefficient of h bar to the g and then a given monomial. So you have to pay a bit attention to the symmetry factors. That's why I put this n-1 factorial, since these x's play the same symmetric role. So let's see what we get. So L starts with h bar dO dxi. That's always there. When it acts on exponential of f, you're putting down some of these coefficients here and eating one of the x. And since I have h bar to the g minus 1, when I act by h bar dO dx, the minus 1 goes away with the h bar here in prefactor. And you have eaten one x, and exactly the one with index I1. So you would get f, g, n, I1, I2, In. It comes from that. Then what happens for the rest? So here we have this xx term. There's no derivation, so it's just a monomial of degree 2. So this I will get if I have 0 power of h bar and a monomial of degree 2. So that makes n equals 3 because I have this shift. And in that case, I would see A, I1, I2, I3. Now I continue. My minus sign here was really in front of everything. Now I have x h bar dO dx. So I have to pull down from the exponential some of this monomial. And then I multiply again by x. If you look at what the power of h bar, what is the monomial that you may have, you're going to find it must come from some fgn minus 1 term. And here you have some index A, some B, I1, IM, A. And here you forget about the IM index. This is because, so in the B is this index, it corresponds to this X which was already present. So it cannot appear in the indices of this monomial here. And the most interesting term is this double derivative, because now you have to pull something down from the exponential. And when you act with the second derivative, either you differentiate that thing or you pull again something down from the exponential. So there's two terms. So either this is, if you look at the powers of h bar, is going to be an fg minus 1 and plus 1. Or when you pull twice something from the exponential, you're going to have two types of terms with their own indices. And you have to split this g into two pieces, h and h prime, and split the set of indices of the monomial to know from which of these terms some of these x's were coming from. Prime 1 plus j, b, j. Okay. And finally, I have h bar di, the constant, which only appears with the power h bar. So it is going to make a di 1 delta g1 delta n1. equals 0. So that's this equation. And what you notice is that first, I mean, FGN is just right there, and I find it is equal to the sum of all these terms. And what kind of indices do I see here? You find that FGN only involves some polynomial in the Fj prime and prime with 2g prime minus 2 plus n prime is smaller than 2g minus 2 plus n. So for example, if you look at this term, twice g minus 1 minus 2 plus n plus 1, this is 2g minus 3 plus n.
Sorry, the red writing is not visible.
Ah, yes, sorry. So let me change the color. Yellow should be better. So for example, this term, sum by induction on 2g minus 2 plus n, we already know it. And as for these terms, the fact that f01 is 0 and f02 is 0 actually implies that indeed these terms will also have 2g prime minus 2 plus h prime smaller than 2g minus 2 plus n. Prime. So if there is a solution to these differential equations, it must be unique because that gives a recursion. And the initial data for the recursion, it's for 2g minus 2 plus n equal 1. And this is f03 is equal to, so g equals 0, n equals 3. We only have this term. And f11, those are two cases which satisfy this, is going to be d. The recursion operator itself, so it's rather the weight that we have here. So this b and this c. So it's given by b and c. So in other words, you start with some collection of PDEs, and automatically pops up for you something which is seems to be related to 2D geometry, because 2g minus 2 plus n, the first thing you think is that this is the Euler characteristic of a surface of G with n boundaries or punctures. And the coefficient of this recursion are exactly the coefficient that appear in the Airy structure. So in fact, the terms in this recursion are in bijection with removal of pairs of pens from the first boundary of a smooth surface of genus G with n boundaries, and this up to diffeomorphisms, preserving the boundary ordering. So for instance, this term here I can think that I have a surface in which I have a pair of pens. And when I remove it, I don't disconnect the surface anymore. So you lose one handle and you gain one boundary when you cut that. Before I had two boundaries, now I have three. And this other type of terms is the case where you disconnect. And then you have to share the genus and the boundaries between the boundary labels here. There are in total n-1 of them here and +1, +1. And this +1 here is coming from that boundary. So that's the C terms. And the B terms, that was Gn-1. And this corresponds to this. Your pair of pen has two boundaries in common with the surface. Okay. The problem is that so far we haven't proved existence. There is you see there's a recursion, but the recursion really makes very specific what is the first index. Whereas all these one play a symmetric role. So for existence of a solution, you have to check that once you run twice this recursion, it doesn't matter which index you choose first, you obtain a symmetric answer. So symmetry is not obvious. And in general, actually, it is wrong. If you take an arbitrary collection of LIs. But let's see what happens for F03. This is the coefficient A. And we would need, so A is obviously symmetric in I2, I3 because of the coefficient of some quadratic form. But there's no reason that A is symmetric with respect to the top index. So you cannot exchange A I1 with I2, I3. So for instance, for G F03 is symmetric if and only if A is fully symmetric. And this is where the second condition in Airy structure comes up. So this graded Lie ideal condition. This is telling you some compatibility. Of this system of PD. Because if there exists some solution to this, then certainly you should have this equals 0. And then you can, so when you commute, what do you obtain? You should obtain a new operator that annihilates exponential of f. And somehow you want this Li to be minimal, generator of the minimal generators of this set of annihilating operators. And if it's of this form, then yes, this is okay because it's a linear combination with on the left the differential operator, on the right some Li's, which are already killing exponential of f. So this is for the hand waving, but existence, it's not very hard. It takes half a page, but it's done in Kontsevich and Soibelman. and is done also in generality. You don't have don't need the degree 2 condition. For any Airy structure, it comes from the graded ideal. Condition. Okay. So the summary, if you have a quantum Airy structure, you get FGNs, which are encoded into the partition function, exponential of f, by a topological recursion, because it's a recursion on 2g minus 2 plus n. And on this side, this is a purely algebraic notion. While on this side, you expect relation to 2D geometry, because the type of recursion you write for FGN is someone writes FGN as a sum over pairs of Pence decomposition. All the
Gaetan,
yes.
may I ask a question?
Yes.
It is ignorance, of course, but is it too long to explain the picture?
Which picture?
Well, the basic picture, this one.
This picture?
Why? Yeah. Why it is okay? It's relation to that recursion.
So I'm only saying.
What is the translation? Yeah.
Yes. So here there's a certain recursion for FGN, and this recursion, it gives a sum of terms, which are all the one we saw here. So these one only appear, the A and the D only appear for the initial case. But as soon as 2g minus 2 plus n is positive, you only have these B terms and C terms.
Mm-hmm.
And I'm saying that, so there's finitely many terms, and they are in bijection with a certain set. And elements in this set have a geometric description, is the set of embeddings of pairs of pans into a surface of genus G with n boundaries, which are bound in the first boundary, like I was doing here. I remove from there. And this up to diffeomorphism. And if you look how can I characterize this set? It's totally characterized by what is the topology of what remains when I remove the pair of pants. And the topology of what remain, the possibility are G minus 1 and plus 1, or this disconnected case, or this Gn minus 1. So far, it's just a bijection of sets between the index set of the terms in topological recursion and this set whose element have a geometric description. What happens is that actually this correspondence is not artificial. And this is demonstrated by the example of applications of topological recursion.
Could I ask a question exactly along
Yes.
those lines? I think it's two questions, and it's the fundamental questions which I think are essential. So what Lyonga described, he didn't go into much detail, but the old approach of Eynard-Orantin and Chekhov involved the quantum spectral curve, first of all. And secondly, each topological recursion problem solved an enumerative problem, a specific enumerative problem, whether it was intersection indices or orbit summers or whatever. So that is my question. What you have, or what Soibelman and Kontsevich have, is a set of rules for defining 4 matrices A, B, C, D.
Yeah.
And for as long as they satisfy these rules, there exists an F.
Exactly. It's an axiomatic approach.
Right.
And
so you end up with equations, which are the TR equations, which are the same as one ends up with the Eynard-Orantin and Chekhov approach. But what I do not see, first of all, in either approaches is how do you match the data to the combinatorial problem that is being solved? And what I don't understand as yet, I suppose you'll explain it, is how do you match the Kontsevich-Soibelman data with the quantum spectral curve?
So here, first, it's axiomatic. So I didn't say yet that quantum Airy structure exists. You could wonder, is it hard to find Li satisfying these properties? And the answer is, it's far from obvious. But that's what I want to explain, how to construct these things. And the second question is here, once you have defined this generating series, this FGN, what does it count?
But can
It's a
you,
very good question.
if you're given a quantum spectral curve, which has certain data, can you read off A, B, C, D, and vice versa?
If you're given a quantum spectral curve, you're also given a normal spectral curve. And from a spectral curve, you can construct some Airy structure. And that's what I'm going to explain in the second talk, I imagine.
But not the converse.
No, because so far, yeah, it's not an obvious thing even to go from a classical spectral curve to get the quantum curve, which is built by the TR, topological recursion, from the classical spectral curve. It's not at all obvious. There's been some progress recently by Eynard and his group, and also Orantin, to treat a larger class of cases. But I would say currently there's no satisfying theorem about the existence of quantum curves for any spectral curve. And in that perspective, quantum Airy structure don't give you much of an advantage compared to the usual spectral curve formalism.
And the second question?
And the second question, indeed, so what I want you to think, and in the third talk, I will try to convince you, I mean, we have some evidence for that because quantum Airy structures are not easy to exhibit. Once you have one, you should be very happy. And being very happy also means that you should expect there is a counting problem behind. For a certain class of Airy structure, and that's what I will discuss in the third talk, there is an intersection theory interpretation. There's a formula for FGN in terms of intersection numbers on the moduli space of curves. But we also have found Airy structure, and some of that's one of the advances that Kontsevich and Soibelman formalism brought, that by trying to cook quantum Airy structure, you forget about the spectral curve aspect. But by representational theory, you can indeed cook some quantum Airy structure that had not been known before, whose spectral curve description had not been known before, and which you would expect, and sometimes we know, sometimes we don't, can also be interpreted as intersection numbers on the moduli space of curves. So here, this is really an expect, and either it's a theorem or it's a conjecture, or a vague conjecture because you don't know what's a class, but I really believe that's a philosophy. There should be some counting interpretation.
But sorry, that's one combinatorial problem, intersection numbers on the moduli space of Riemann surfaces. But you're saying all of these correspond to such a problem?
Well, then, of course, you have many other types of counting curve problems. You have Gromov-Witten theory, you have counting maps, you have counting Hurwitz numbers. There, I would say it is, you see, these are little islands. And so far, for many, we know that it satisfies topological recursion, but we don't know it for everything. If you take compact Calabi-Yau's, for example, we don't know if it satisfies topological recursion. But these are little islands. This formalism, I would say, is the general box into which give you some conceptual understanding of what is the nature of topological recursion. And then if you really want to prove that some specific problem satisfies topological recursion, you have to work, and in each case which is known, in each application, this is some amount of work, and there's no general strategy to do that. There's various strategies, but not always the same has been successful.
Okay, let me, before you recoup and continue, to slip in my last inevitable question.
Mhm.
Does e to the f satisfy Hirota bilinear equations?
So I would expect that in general, no. I would expect that the solution of the topological recursion are not necessarily tau function of integrable hierarchies, but there would be an important subclass that is, in particular, the one that come from compact spectral curves. I would expect, and there are some partial results into that this gives a tau function. But in general, for arbitrary quantum Airy structure, I don't expect it's a tau function. Not only that I don't know how to prove it, but I don't expect it's true.
I have a quick question. Why is it called airy?
Ah, yes. So there's two reasons. First, the trivial example of Airy structure in dimension 1. It looks like that. And this is a bit too complicated, so let's set everything to, these are constant, and let's set everything to 1. Then the solution, there's only one operator, so there's no consistency relation. Then exponential of f can be written in terms of the Berry function. So I forgot what are the constants here, but there is something. So that's the first reason. The second reason that there's a more interesting example where V is the loop space. And in that case, you can take Li to be the Virasoro operators. So the Virasoro constraints for Gromov-Witten theory of a point. That is just intersection theory on MGN bar of the psi classes. And in that case, this exponential of f is the Witten-Kontsevich partition function. So expressed in terms of psi classes, and Kontsevich had proved that this is the matrix Airy function. It's some infinite determinant built out of the Airy function. So that explains the name. Strictly speaking, it's only justified when your operator is degree 2. But yeah, in general, one would call maybe higher Airy structures for the things of higher degree. And I must say, actually, since it's you asking the question, Philip, if you don't put this condition, the solution is the Whittaker function, is some Whittaker function. And you can also, in general, obtain some Whittaker modules from more interesting quantum Airy structures. Okay. Should I continue?
Yes.
May I ask you a question?
Yes.
Okay, so yeah, you just said here, but okay, so you're now taking an example with maximum degree 2. But yeah, my question is that do you have a similar geometric perspective for the higher operator?
Yes.
Maybe you will explain, but
you just so higher degree. Where's the pen? You may just, instead of removing pairs of pens, you remove spheres, or maybe some genus surface embedded, starting from the first boundary. So you can have many connected components. You may even have something like this that is branching. And the terms now are in bijection with these embeddings of subsurfaces with strictly greater Euler characteristic, starting from the first boundary in a smooth surface and this up to diffeomorphism.
okay, so you mean you still have a recursion, recursion relation, right?
You still have a recursion relation, there's just more terms, which can be interpreted in this way. You don't only remove pairs of pens.
Okay, thanks.
But it still has the same linear quadratic form.
No, it's not anymore quadratic, because as soon as you remove, for example, a sphere with 4 boundaries, you can have a term like this, where I have 3 connected components. And so this is an FFF. And it's exactly come from terms like this in the Airy structure. And if you go higher, you have higher order terms. Okay. So the good point about having 3 talks is that I don't have to worry if I don't finish today, because I don't want to go much faster, since it was supposed to be some introductory lecture. So we'll just take the time that we need. Okay, so now I want to show how to actually construct Airy structure. It's not obvious at all. So if you know the Chekhov-Eynard-Orantin topological recursions from spectral curves with simple ramification, you would indeed find, just translate the residue formula from topological recursion. You can translate it into some Airy structure, which is of degree 2, in maximal terms of maximal degree 2, and which is based on the Virasoro algebra. So this was some of what was known from the start of the topological recursion, that this solves some Virasoro constraints. And what this idea of Kontsevich and Soibelman brought is that you have to find Airy structures, and a good way to do that, and actually that's back from some work of Milanov. So he was the first to try to match W constraints with some higher order topological recursion. And what he did in a specific case, in fact, can be made a general strategy, and that's what I want to explain now. So what you should, so if you don't, I'm going to go into the detail, but if you don't follow the details, what is to remember that take a vertex operator algebra, so it's a certain description of chiral CFT. You can allow some automorphism of this vertex operator algebra. And you just need to have some free field representation. That is a representation of your VOA by some differential operators. If you have that, then you're in good shape to apply the general strategy, which may or may not give you Airy structures. That's whether you find some or not, and which one you're going to find by computing. So that's what I want to explain. And for the organizers, please stop me when the time is over. I'll just continue next week. Okay, so what is a VOA very roughly? Oops. This is a Z-graded vector space. Oops. V, which is equipped with a map. So which is called the state field correspondence. So this is called the state space. And that's a linear map from V to endomorphism of V, but valued in by infinite formal series. So infinite in both directions. So you can't really multiply them in general. So you need to have that, which is called the field. You need to have a certain distinguished vector, which we denote in this bracket notation, such that when you look at the corresponding field, this is the identity, it doesn't depend on Z. And if you look at any field, and that's an endomorphism of V valued in formal series. You can always apply it to the vector 0. I mean, not the null vector, but this bracket 0. It must be the identity up to something of higher order. Then you must have another distinguished vector whose field, so you can decompose in the formal series in Z and Z inverse. And the Ln must satisfy the Virasoro commutation relation for some central charge. And normally L-1, so it's the central extension of the diffeomorphism of the Lie algebra of the diffeomorphism of the circle. So L-1 normally correspond to translations. So here, this L-1, so it's some endomorphism of V. So you can act on any vector. And on the field, it just acts by differentiation. And finally, there's some axiom of locality, which is extremely important, but since I'm not lecturing on VOA, really, I'm not going to write it down. And I need some vocabulary. The conformal wave, if you have an eigenvector of L0, which is the correspond to dilation operator in terms of the Virasoro, so we call the conformal wave the eigenvalue for L0. Okay. And in that case, if I have some vector V with conformal wave delta V, the corresponding field, we're going to denote the corresponding coefficients, so which are called the modes, like Z to the, so it's convenient to shift by the conformal wave here, plus N. And once you have a VOA, you can look at a suitable completion, which I'm not going to discuss, of the associative algebra of modes. You look at the modes of all the vectors you can imagine. That's a certain subspace of endomorphism of V. And that gives you some associative algebra. And you have to complete to do that. Okay. So what I want to do now is so this program, the general philosophy, it has been realized for certain VOAs. And I want to explain in detail how it is done for WGLR. So I have to explain what are these W algebras. So, okay. First, I have to start with the Heisenberg algebra. And I will do that just for GLR. So there's a certain Cartan Lie algebra attached to that. So it's C to the R in this case. And it's equipped with a killing form. Here. And from this, we can build the Heisenberg algebra, which is a Lie algebra, so H hat, which is formal series, and then extended by some central element. And so K is going to be central. And if I have some Xi, which is in a Cartan, I'm going to denote psi n to be psi tensor z to the n. And so I declare a Lie algebra structure by setting psi n eta m for any psi eta in the carton will be n delta n plus m0 and the killing form applied to psi and eta. And for what we do in Airy structure, it's convenient to rescale the killing form and introduce some h bar. So strictly speaking, here I have to extend by h bar. Good, so that's the Heisenberg Lie algebra. Now we can consider h minus, which is just the span of all the psi minus L for L positive and psi an element of the carton. And we can consider a vector space which is spanned by symmetric polynomials in elements of h minus. And so there's it generated by, there's some base vector and then you just act like polynomial. And this has a VOA structure. So to specify it, I need to define the map Y. What is the field? So you do it by the following formulas. If you have Y of psi placed in degree -1, you define this to be psi n over z n plus 1. So the Heisenberg is acting on itself. So is acting on this. So this makes sense.
Gaetan,
Yeah.
I think we have 5 minutes left. So
Okay.
Yeah.
Yeah, I will respect that. Then, so this is only for this. So what do you do when you have some polynomial like this? Where this psi I1, psi I n are elements of the carton. We declare that to be the normal ordered product of d ki minus 1 z over ki minus 1 factorial and then y psi I j placed in degree -1. Okay, and the normal ordered product here it means that plot the modes in each monomial that you may have in this product, plot the modes with positive indices that is some psi n with n positive to the left and negative modes to the right. And this satisfies all the axioms of VOA. I just have to specify this Virasoro vector. And it is here where chi I is an orthonormal basis for the carton. Okay. So in the last 2 minutes, I will say, what's the crucial ingredient? Why do we consider VOAs? is because we have this associative algebra of modes, and we want to find some interesting ideals, graded ideals inside them. So yeah, that actually may be for next time because I have to define still what is the W-algebra. So WGLR, it is the sub-VOA of the Heisenberg VOA, which is generated by EI chi1 chi n placed in degree -1. So these are, this chi I is an orthonormal basis for the Cartan. So these are elements of the vector space V. And I can form polynomial, that's the element of V. I place in degree -1, and this EI is the elementary symmetric polynomial. So that means, what are the different fields and modes that you have? You take this, so let's call that EI. And you take the state field correspondence, this Y coming from the Heisenberg algebra, so which you could compute by these formulas. And you put EI, and that defines what I will call WIZ, which are your, which is conformal with I. And you take that as defining your W algebra. And you get a VOA, which has central charge. C equal R, the rank. Okay. So that's, we want to consider the algebra generating by that. And next time we're going to see how we can find interesting ideals. So just select certain modes, which somehow close under a commutation relation by this graded ideal condition. And also how to get some free fields of representations of those by differential operators. And that will allow us to construct Airy structures. I'm stopping here for today. Thank you.
Thank you very much, Gaetan. Let's thank the speaker, first of all, for this nice talk. And so, do anyone has any questions? But today we are going to record the question part. So if Gaetan don't mind and
no, you can go ahead.
Participants are okay with that. So let's go to the questions part.
Gaetan, may I ask you a question about examples? Are you going to present some concrete examples?
Yeah, that's what I want to go. So today, actually, I wanted to construct the examples of Airy structures, but then the last talk should be about, I hope I will arrive there, but at least I guess I will give a summary if I don't manage to give the details, I will present this theorem that for a large class of Airy structures, there is an intersection expression for FGN. And therefore, you can think of that as an application. For example, if you want intersection theory of the Hodge class, of course, it is known that there is the ELSV formula. And it's represented in terms of Hurwitz numbers, and we know topological recursion for that, the specific spectral curve. But it fits very naturally in this theorem, which in that case is due to NR. And I will also give generalizations of that. But for that, I apologize that you may have to be a bit patient till the end.
So
okay.
Sorry. Is there a quantum Airy structure associated to any cohomological field theory? Is it what you said?
Semi-simple, yes.
Okay.
This is essentially So of course, spectral curve topological recursion is embedded into the formalism of Airy structures. Therefore, the theorem of Doss, Dulin-Barkowski, Orantin, Chardin, and Spitz from maybe now almost 10 years ago is telling that any semi-simple co-FT can be represented, intersection numbers can be computed by topological recursion on a certain spectral curve. So you do have a quantum Airy structure corresponding to that. Actually, it's degree 2. It's based on the several copies of the W-algebra algebra. And you can understand very nicely in terms of Airy structures the action of the given tile group. And some of that's in the modern way, you can shortcut a lot what they assembled 10 years ago.
Okay, thanks.
And maybe can I add that there are also non-semi-simple co-FTs that can be captured in this formalism?
That's true. There's some examples of non-semi-simple co-FT, but then the problem is that you cannot hope to have all non-semi-simple co-FT because you don't have given tile group acting transitively. So you cannot hope it to act transitively, so you're a bit stuck if you start from a given one and you want to match it. The good thing is that as soon as you have put one co-FT in the formalism, then you have a whole class of co-FT obtained by symmetries. And the symmetries, you do see them from Airy structures. That's also going to be maybe end of the next talk, or maybe the third. I will talk a bit about that.
One question. Are the Airy structures for logarithmic variables or Q difference equations?
So it depends what exactly you mean. If you just take, I don't know, Q difference equation, or when you have log variables, and you consider the corresponding classical spectral curve. This is a plane curve, which is not algebraic, but any plane curve which is smooth and has simple branch point is going to give you an Airy structure of order 2 based on several copies of Virasoro. If the curve has higher order ramification points, or if the curve is not smooth, especially not smooth at the ramification points, then I will also actually give the result about that. That's something that we did with Rainier and Yannick Schüler. You also can construct some Airy structure, but there's actually the type of singularities of your curve is constrained. You cannot always do it, and it's a bit surprising. We don't know what happens for these pathological curves.
So could there be Airy structures for knots?
Yeah, well, you have a spectral curve for knots, the PSL2C character variety. So you'd certainly have an Airy structure for knots.
Ah, okay. Thanks.
May I ask, is there any kind of gauge group action on the Airy structure? Because it seems to be like an... Yeah, and...
So there's a lot of symmetries.
Gaetan, you stopped
we
screen
can't see you.
I'm going to reshare my screen if you allow.
You probably can do that.
You have to join the Zoom. You have to join the tablet.
Mm-hmm.
Okay, you have to allow the tablet.
Yeah. I will allow you in a second. Yeah.
Yep. Okay. So now you should see. Good. So we have an Airy structure as a map from here to here. And of course, you a priori have, well, automorphisms here, which are exponential conjugation by differential operators. That you can always do, but it may not respect always the Airy structure property. So this always respects the Lie ideal condition because it's a conjugation, so commutation relations are preserved. So 2, but for 1, it can break. So if you have this in degree 1, well, you may, for example, you may do, that's an automorphism. You replace d over dxi by xi and xi by minus d over dxi. And that's going to convert it into this, which you don't like.
Okay.
However, there's a subgroup here, which you can do. And it's the one which takes, oops, I need the white. If you do this, yeah, and so this is a scalar, I1, In, and then you just take pure differential operators. And in the way I want that, so of course I may be slightly wrong with the grading, but this is not so important. If you adjust an exponential of pure differential operators, that is going to preserve 1. And so these are symmetries of Airy structures. And there's 2 which are important. So for the first one, there's some subtleties for it to be well defined, but morally, if you have something like that, it corresponds to translations of variables. And you have this one. And this, so this is well known when you do deformation quantization of symplectic vector spaces. This corresponds to change of polarization. And it amounts to cent. So this remains, but this is going to be some xi plus phi a phi ij. Like this. And this preserves the commutation relations, I mean the Weil commutation relations, because this guy commutes with this guy. And so this is an important symmetry, and the given Thaler group actually is sitting inside there. In the R action of the given Thaler group. If I want to simplify a little, it's a subgroup in there.
And how such gauges affect the recursion relations? They probably are not invariant with.
They're certainly not invariant. So let's call that U. And the equation you're solving is L exponential of f is 0. And now L has become conjugated. And so that's your new partition function. So you have to take this exponential of purely differential operator and let it act on this sum of FGNs. So you're going to have Feynman graphs. The old FGNs will be at the vertices. And they're going to be joined together by some, so if you just have this quadratic thing, you have propagators, and that's the weight of the edges. If you have higher order things, then actually vertices, not only 2 vertices come together, you have rather a face involving a certain number of vertices corresponding to the degree of this differential operator, and a certain weight, which is the coefficient that you will have in front.
Thanks. Yeah. Okay, any more questions?
Let me ask one more question.
Sorry.
Okay. Probably you will explain next lecture, but about the connection between the Airy structure and double algebra. But is it possible to discuss the double algebra with a generic central charge? You mentioned that the C equal R, which is a free Fermi point. But,
yes, so it is possible. In general, so the philosophy that you can retain is this. And so here, if you do WGLR at any central charge, the only difference is that you may just have less automorphisms. So if you do central charge different from R, of course, you have the Murat transform that gives you the free field representation. And you don't have much automorphism. You just have the automorphism of the Dynkin diagram, so 0 to Z. So also in this what's called self-dual central charge, there's more automorphism, and it's interesting to look at twisted representations using those automorphisms. And it's exactly what you need to match with the Chekhov-Eynard-Orantin topological recursion. You can also do it for arbitrary central charge without this twisting. And this is something we're doing currently with Nitin, Chidambaram, Vincent Bouchard, and Thomas Creutzig. And this gives you some Whittaker vectors. But somehow it was not, okay, I can put it this way. There was something called non-commutative topological recursion, which had been developed in certain cases by Eynard and also Marshall. And I think Raphael Béliard also had some take in it later. And somehow but the theory, I would say, is not complete or not completely written. But here, when you do this WGLR without twisting as arbitrary central charge, somehow you exactly find the Airy structure lurking behind this. And you find it without having to guess much. You just compute from Murat transform. In particular, the important thing, which is not at all obvious when you write this non-commutative TR, is whether you get something symmetric from the recursion relation. And here it is provided by the fact that you have an Airy structure and by this theorem, which I stated here, which is Kontsevich and Soibelman, and whose proof is not too hard. If you want to prove it by hand that the thing is symmetric given your recursion, good luck. I mean, I don't know how to do it. So that's why this modern way is interesting.
Yeah, from this point of view, it looks like the beta deformation is very possible from this Airy structure point of view.
Yeah, exactly. The beta deformation corresponds to this arbitrary central charge.
Yeah, I see.
We hope. Okay, I don't know when we'll finish the paper, but yeah, it may take a couple of months.
Okay, thank you.
Okay. Do you know if there is a relation between a quantum Airy structure and the Dubrovin-Zhang hierarchy associated to one cohomological field theory?
So I would say in this framework, the relation to integrability is not so well understood. That relates to my answer to John at the beginning, that for the moment, I would say you don't gain so much from working with Airy structures compared to working with spectral curves to discuss integrability questions. In some simple Airy structure case, like this one related to Witten Kontsevich, you have a good understanding because, okay, there's some relation between Virasoro constraints and being a KdV tau function, which are well understood. In that particular case, you can really build a Kac-Schwarz operator from the Airy structure. So Vincent Bouchard and his students play a lot with that. I think Helder also played with that. But these are quite specific examples. I wouldn't say that you have such a geometric thing really over Frobenius manifolds. You don't really have that for the moment here. I don't think it's impossible, it just doesn't exist yet. The progress about that question, I mean, it's related to constructed quantum curves, proving integrability. The recent progress has rather been done by using the usual residue formulation and relation to the moduli space of flat connections. That's the approach taken by Orantin and Marshall. And Eynard and Garcia-Failde had a paper at the same time with a slightly different approach, where they go in this direction of quantum curve and so on. And that's also a way to go in direction of integrability. And they just compute by brute force from the topological, from the residue formula.
Okay, thanks.
If there are no any questions, I will stop recording now.